Okay, so today we're going to finish off chapter 4. Um, hmm, hmm. Hold on, I'm stiff today. So, the chapter 4 homework will be due on the 29th. The quiz will be on the 27th. That's not next week, it's the week after. That's because David's going to be on the 29th. The exam for chapters 3 and 4 will be on the 29th as well. So you have a bit longer for that material. You can see this all in the schedule on Blackboard. So, so just some review. Work is force in the direction of movement times the distance. So work is force times distance. Kinetic energy is energy stored in motion. So it's 1/2 mass times velocity squared. And the work energy theorem is the change in work is equal to the change in kinetic energy. So final kinetic energy minus initial kinetic energy equals 1/2 mv final squared minus 1/2 mv initial squared. And that will equal force times distance. Potential energy is the energy an object has because of its position, due to its position or location. It's the energy stored in position. So the energy stored in, lifting something up, you store some energy in and you get it back out by letting that thing fall. Most potential energy is due to gravity. That's the only kind we're going to cover in this class. But there's also potential energy in springs and other things. There's electrical potential energy and all kinds of other things like that. But in this class, we're going to focus on just gravity. Work is force times distance. So weight is a force, mg. So potential energy from gravity is mgh, mass times g times height. And energy is conserved. It can be neither created nor destroyed, but it will change from one form to another. It's always conserved, and the total energy of an isolated system will remain constant. That was sort of what we were trying to show in the lab today, but because of error and stuff, the numbers, actually, they weren't too terrible except for the last one. The last one was off. But the total energy doesn't really change with time. And so to simplify, we'll deal with ideal systems where energy is only in the form of kinetic and potential. So you'll basically have 1/2 mv squared plus mgh at time 1 equals 1/2 mv squared plus mgh at time 2. Now, power. Power is what we're going to talk about today. Power is work over time. So power is work over time. So that is force times distance over time. And distance over time, that's speed. So under certain circumstances, power is force times velocity. Force times speed. The SI unit for power is the watt, joules per second. So 1 watt equals 1 joule per second, or 1 kilogram meter squared per second cubed, if you want it written out in base units. And don't confuse work with watts. Basically, physics ran out of letters a while ago. So if you use a force of 1 Newton to raise a mass a distance of 1 meter, the amount of work you do is 1 joule. if that was done in a time of 1 second, then the power is 1 watt. So a quick review of the SI units. Force is newtons. The units are kilogram meters per second squared. Work is joules. That's Newton meters, newtons times meters, or kilogram meters squared per second squared. If you think about energy being, kinetic energy is 1/2 mv squared, kilogram meters per second squared, meters squared second squared. Oh wait, no, this is energy is also in joules because work is just energy moving between things. And power is work over time. The unit is watts, which is joules per second. In the British system, because work is foot-pounds, power is foot-pounds per second. But a more commonly used unit is horsepower. Horsepower was invented by James Watt and defined to be 550 foot-pounds per second when he was selling his steam engines. It was based off real observations, so it wasn't like insane, but actual horses vary a lot. So and the greater the power of an engine, the faster it can do work. So a 2 horsepower engine can do twice as much work as a 1 horsepower engine in the same amount of time. So if you use a constant force of 150 newtons to push a student's stalled motorcycle a distance of 10 meters along a flat road in a time of 20 seconds, we want to calculate power. So this is going to be force times distance over time. Force is 150 newtons, distance is 10 meters, time is 20 seconds. The power is work over time, or force times distance over time. 150 newtons times 10 meters over 20 seconds, 75 watts. A student expends 7.5 watts of power in lifting a textbook 1/2 meter in 1 second. How much work is done and how much does the book weigh in newtons? So here we're starting with power and we're working out work. So work will just be power times time. And then we're going to work out the force, because remember, work is force times distance. So power is 7.5 watts, the distance is 0.5 meters, the time is 1 second. Work is just going to be power times time. So, work is power times time. So 7.5 watts times 1 second is 7.5 joules per second times 1 second, or 7.5 joules. And weight is a force. So force times distance equals work. So force is work divided by distance. So 7.5 joules divided by 0.5 meters gives us 15 newtons. So the work done is 7.5 joules and the book weighs 15 newtons. Now, electrical energy used is again going to be power times time. In our day-to-day life, we tend to measure this in kilowatt hours. Kilowatts times hours. Now, we could measure it in joules. That would be watts times seconds. But we do measure it in kilowatt hours. A lot of electrical things are in something hours. Like batteries are, the charge that batteries can give off is measured as, like amp hours or milliamp hours. You may have noticed on a battery. But you could actually just use the unit of charge, which is coulombs. which is an amp second. But so kilowatt hours. So kilowatt hours, you pay your electricity in kilowatt hours. You could pay your electricity in joules and megajoules or something. 1 kilowatt hour, because a kilowatt is 1,000 watts and an hour is 3,600 seconds, is 3.6 million joules or 3.6 megajoules. The 1 kilowatt hour is 1,000 watts times 3,600 seconds, or 3.6 times 10 to the 6 joules, or 3.6 million joules, or 3.6 megajoules. So if you have a 1 horsepower electric motor that runs for 10 hours, how much energy is consumed in kilowatt hours? Well, let's find the energy. The first step is going to be converting from horsepower to watts to kilowatts, because we want kilowatt hours. We know the time in hours. We want our power in kilowatts. So 1 horsepower times 746 watts, so that's what 1 horsepower is, times 1 kilowatt per 1,000 watts is going to be 0.746 kilowatts or 0.75 kilowatts. 0.75 kilowatts times 10 hours is 7.5 kilowatt hours. You can see the watts cancel here. If I use 55 newtons to push a box a distance of 5 meters in a time of 22 seconds, how much power am I producing? So here you have a force, a distance, and a time. Yes, okay. Making sure I hadn't forgotten to start recording. So power is work over time. Work is force times distance. So power is force times distance over time. 55 newtons times 5 meters divided by 22 seconds is 12.5 watts. If it takes a 2,500 watt oven 30 minutes to cook a pizza, how much energy is necessary to cook the pizza in joules and in kilowatt hours? And there are some conversion factors here. 1 minute is 60 seconds. 1 hour is 60 minutes. 1 kilowatt is 1,000 watts. So power is energy over time. Energy is power times time. So let's start by doing conversions. We're going to want time in both seconds and hours. 30 minutes is 1800 seconds. I'm just multiplying by 60. It's also half an hour, 0.5 hours, dividing by 60. So to find the power in joules, we have 2,500 watts times 1800 seconds. That's 4.5 million joules. 4,500,000 joules. We can also do the same thing. Now we can figure it out in kilowatt hours. First, we need to figure out what 2,500 watts is in kilowatts. That's 2.5 kilowatts. Just divide by 1,000. So 2.5 kilowatts times 0.5 hours gives us 1.25 kilowatt hours. And lastly, we can check that those are the same. We can do the conversion. 1.25 kilowatt hours times 3.6 times 10 to the 6 joules per kilowatt hour gives us 4.5 times 10 to the 6 joules. So 4.5 megajoules or 1.25 kilowatt hours. Those are the same amounts. But your electric bill will be in kilowatt hours. So how high can a 1 horsepower motor lift a 15 kilogram mass in a time of 2 minutes? Oh yeah, I definitely should change the numbers on this one. So 1 horsepower is 746 watts. 2 minutes is 120 seconds. Work is power times time. But work is also force times distance. And that's the weight, mg, times the height. So power times time equals mgh. So if you solve for height, height is going to be power times time over mg. And I really should have increased the mass here to 150. So 746 watts times 120 seconds is 15 kilograms over 9.8 meters per second squared. The height in question is 609 meters, which is a little bit ridiculously large. And in fact, I'm going to quickly change this So it is 150. Because that number is ridiculous. Point. There it is with 150, because 150 makes it 60.9 meters, which is a lot more reasonable. But yeah, 1 horsepower is actually a lot of power. So how much power is expended by a 60-kilogram man climbing 15 meters in 30 seconds? So running up 5 flights of stairs, basically. So power is work over time. Work is force times distance over time. So this will be mgh over time. So 60 kilograms times 9.8 meters per second squared times 15 meters. The change in potential energy over the time, 30 seconds. The power is 294 watts. If it takes 100 newtons to keep a car traveling at 11 meters per second, how much power is the car using to do so? The power is work over time, force times distance over time. So force times distance over time, and distance is speed times time. Power is work over time. Work is force times distance over time. So that's force times speed times time over time. Time cancels. You get force times velocity, so force times speed. So 100 newtons times 11 meters per second. You can also just choose a time. You can plug in like 1 second. And you get 100 times 11 times 1 divided by 1. So it's 1100 watts. So energy, we're dealing with energy. No matter what type of energy we speak of, chemical, electrical, mechanical, the main unifying concept is that energy is conserved. It is never created nor destroyed, but you can change it from one form to another. So there's several types of energy. There's thermal energy, heat energy related to the kinetic and potential energies on a molecular level. That's what we're going to cover in the next chapter. It's all about heat. There's gravitational potential energy. This is stored gravitational energy associated with an object's position. There's electrical energy associated with the motion of electric charges. There's chemical energy associated with molecular bonds. There's radiant energy associated with electromagnetic waves from the sun. There's nuclear energy that comes from the rearrangement of atomic nuclei. You can break apart larger nuclei via fission to generate power, or you can glom together smaller nuclei to generate energy. As long as, if you're going up towards iron, you get energy out in theory, or if you're going down from something heavier towards iron. The most stable nucleus where you don't get energy anymore is at iron, turns out. We can effectively use fission to generate energy. We cannot effectively use fusion to generate energy yet. The sun does it for us just fine. It fuses hydrogen into helium, but it cheats by having enormous densities and pressures that we can't generate on Earth safely. Enormous densities, pressures, and temperatures we can't safely generate on Earth. Yeah, and then, so there's a few things. There's like fossil fuels. Fossil fuels are things like oil, gas, and coal. They come from once living organism. They're basically stored solar and chemical energy. Oil and gas comes from dead marine life, mostly single-celled stuff. And coal comes from long dead plants. The oil is from marine organisms. These numbers for amounts might be off. I don't think we import more than 50% of our needs anymore, but we do still import quite a bit. Gas is also from marine organisms. In fact, we export gas. We produce more gas than we use. Coal comes from terrestrial land plants. The US has large reserves, but there are environmental problems with coal mining. And there's methane hydrate, which is a crystalline form of natural gas and water. There's some research on possible usage as a power source, but most of the research at this point is to make sure it doesn't spontaneously get released, because that would be bad. So here are some examples of power. There are, and all the data in these slides is like significantly out of date, because these are old. The book's data is old. And I think I'm using an older edition. I don't know. I think I updated them, but I'm not 100% sure. They're still a little dated. But so here's fossil fuel. These are pump jacks pumping out oil. You don't need a dramatic pump for gas because it's under pressure. So this is a Christmas tree wellhead for a gas well. It's not very impressive looking. You drill a hole in the ground and the gas comes out and you catch it. And then you send it in a pipe underground somewhere else. This is a coal bed. So this is the fossil fuel coal bed. Pretty much all the coal was put down about 300 million years ago. And here's energy in a renewable form of chemical energy, the food. So this is US fuel consumption. This is definitely out of date. But so this is oil, natural gas, coal. I think coal has gone down. Natural gas has gone up a little. Nuclear, I think, has gone down a little, and renewables have gone up quite a bit. Mainly because solar got cheap. And then for fuels, for electrical generation, coal has gone down, natural gas has gone up. Nuclear, I think, has gone down a little. I think hydroelectric and oil are about the same. And again, other renewables has gone up. Because again, solar got cheap, a lot more wind farms, things like that. Energy consumption by sector, industrial is about 32%, transportation is about 29%, residential is about 22%, commercial is about 17%. Now, alternate or renewable energy sources are generally preferred to fossil fuels because they don't generate CO2, which is leading to climate change, which is how, why we've been having more severe weather and other unfortunate things. So renewable energy, alternate energy sources are energy sources not based on fossil fuels or nuclear processes. We really should have more nuclear, but people are stupid about nuclear power. Renewable energy sources are energy sources that cannot be exhausted. So the wind, the sun, and in large part, these things overlap. So hydropower uses the gravitational potential energy of water flowing downhill due to gravity. Now, biggest problem with hydropower, all the good dam sites are taken. And a small hydropower installation just isn't worth it. In fact, there's a bunch of like abandoned old ones out there, which are actually causing problems. Building a dam causes significant environmental and ecological damage because you cut off the flow of a river, you redirect the flow of a river, and you flood a big area behind the dam or above the dam. It tends to cause significant loss of agricultural land because a lot of agricultural land is in floodplains or in along rivers. Here's an example. This is the Flaming Gorge Dam in Utah. Wind power. The biggest negative to wind power is that it's not particularly aesthetic. There's some. The other thing is it has to be located where the wind is sufficiently constant and strong enough. It has minor environmental effects. It's been used for thousands of years to grind grain and pump water. But wind power is a decent thing. It has the big problem that most renewables have is that your power is not generated on demand. So you get power when the wind is giving you power, but our electrical grid has no way to store energy, or basically no way to store energy. And that's sort of the problem. So things you can adjust the rate, because you have to adjust the power generation to match the power consumption, or else the grid breaks. So one of the things we need is grid storage, and we're working on it, but it's hard. So here's a wind farm. You'll notice that all windmills, modern windmills, have 3 blades. Turns out there's a reason for that, sort of a balance between efficiency and cost. And you want an odd number. It turns out you want an odd number of blades because they end up quieter. But yeah, big wind farm. Solar power. Solar power has been the best thing recently. It's a big future source of reliable and economic energy. That's a little dated. Now there's a lot more solar power in use. Because solar power just got cheap. So you could just stick it on top of your warehouse or whatever. It's not very expensive to build a big solar farm like this. Just putting out a whole bunch of solar panels. And so, but the big problem with solar power is that it only generates energy when the sun is shining on it. So again, the problem is storage. we use energy at different times than when there's the most sun. Yeah, the peak of the sun is the middle of the day. The middle of the day is actually the least use energy-wise. Now, geothermal energy is great, but it's incredibly site-specific. If you and it So there needs to be a large natural change in temperature as you drill, as you go down. And the problem is figuring out if that's the case. I mean, certain places you just know that's the case because the geology is such that there's going to be a big natural change in temperature, like Iceland or Hawaii. You know, you're sitting on a magma bubble, basically. But in other places, there might be, but there might not be. But finding out is really expensive. And in general, if you could dig deep enough, cheap enough, it would be viable most places. But drilling is expensive and it's hard to get deep efficiently. So, I mean, the big problem is that there's a big capital outlay and finding out if your site is worthwhile is expensive. And so once you've got it, it's great, super cheap to run because you're just running off the heat of the earth. You're barely expending any money to run your power plant. But to get there gets tricky. It's very site specific. It's extensively used in Iceland. So electrical power is dirt cheap in Iceland. People heat like greenhouses by just drilling down, running water through the ground and back up. You know, people have their own personal geothermal power in Iceland. But that's not that common. Not many places are like that because Iceland is sitting on a place where two continents are separating. So there's lots of heat coming up. Here is an example of a geothermal plant. This is Puna geothermal plant in Hawaii. Hawaii is on a magma bubble. Geothermal energy is easily accessible there. Here's an example of an active volcanic flank from the big island of Hawaii. You can see this is where molten lava is falling in the ocean. It's not hard to guess that geothermal energy would be effective around here. The Yellowstone area has tremendous amounts of geothermal energy. It's just not terribly economically viable to tap it because there's just not that many people around there. It turns out. But it's on another magma hotspot. So yeah. Now, tidal energy is steady, reliable, and predictable. But to tap it, you need to design your thing to handle the fact that the tides are bidirectional. You have to generate energy from water flowing one way and the other way. So tidal currents have been generating electricity along the Rance River in France since the 1960s. You have to have a place where you have big enough and fast enough tides. So that's sort of geography specific. And it's in the ocean. And it turns out putting things in the ocean is a pain in the butt because stuff will just grow on them and reduce your efficiency. But here's the basic idea. You have big turbines underwater. That generate electrical current using tidal currents. It's just the ocean is a really nasty environment, it turns out, which makes things more complicated. But there are a few places where they do this. But yeah, you have to set them up so at least one design I've seen, you can raise them out of the water to be cleaned. And then there's biofuels. So things like corn, sugarcane, and other plants can be used to make ethanol, which is an alcohol, which then goes in our gasoline. Used to provide gasoline in Indiana. So ethanol can be mixed with gasoline and used as a fuel for cars. In Indiana, all the gas is 10% ethanol. At least that's what you see on the sticker. And then if you've seen E85 or something, gas, that's a much higher concentration of ethanol. Up to 85%. It varies technically, and that you need to have a car that's able to use it. It turns out it's not like an issue with engines. Ethanol burns in engines just fine. You have to have all your hoses replaced with stuff that will not dissolve in the ethanol. That it turns out is the actual problem. Like the modification to make your car a flex fuel car that can take E85 is basically just replacing all the hoses with hoses that will be degraded by ethanol. But depending on the plant process, however, more energy can be used in the production of the ethanol than supplied by burning. Some of this is to use up all the frickin' corn we made. But there's reasons we make lots of corn. It has to do with the economics of farming. But yeah. So biomass is just stuff. Any organic material like agricultural crops, wood, animal waste, municipal waste, aquatic plants, etc. And you can set it on fire. And thus you can burn it for energy. And this is a renewable resource. And it's generally a carbon neutral resource because the carbon was sequestered in making the plants and then you release it again by burning it. And therefore it generates energy. And just most of the carbon you would have would be released by letting it rot anyways. So here are the important equations for chapter 4. Work is force times distance. Kinetic energy is 1/2 mv squared. The work energy equation is work is equal to change in kinetic energy. So 1/2 mv2 squared minus 1/2 mv1 squared. Potential energy is mgh for gravity. Mechanical energy can be conserved. So kinetic energy plus potential energy at time 1 equals kinetic energy plus potential energy at time 2. Power is work over time or energy over time, and that's force times distance over time. And for like a dropped object, velocity ends up being 2g delta h, solving this conservation of energy equation. Square root of 2g delta h. Yeah, and here's the same things again. I don't know why I have this slide duplicated, but these are the important equations. Well, that's the end of chapter 4. So I'm just gonna end lecture. We'll start chapter 5 next week. If they aren't available yet, they should be soon. Your midterm grades should be up soon. I submitted them last night. They were due this morning, so they should, enter the system soon. I don't know how long it takes for them to become visible to you, but they're in. I can't change them. The biggest thing that dropped people's midterm grades was not doing homework. But that's sort of a general thing between multiple classes. But yeah. And remember, on the homework, you can always request an automatic extension and do it late so you can bring your grade up. That's about it.